So welcome everyone to our data science and computational statistics seminar. It's my great pleasure to introduce speaker today, Oanh Nguyen. So I will introduce her. So Oanh obtained her PhD from Yale in 2017. She then spent 3 years as instructor at Princeton, and she is currently an assistant professor at the University of Illinois at Urbana-Champaign. So one research interest include random functions, stochastic processes, and random graph. So today, Oanh will tell us about her work on roots of random functions. So during the talks, if you have any question, you can simply unmute yourself to ask Oanh directly, or you can type in the chat box. So I hope that's clear. So now to welcome Oanh, please. Can you share the screen?
Yeah, thank you, Han, for the introduction. Yeah, and thank you for inviting me. It's a great pleasure to give a talk at the seminar. Let me share the screen. Okay, so for today, I will talk about my research on random functions, and let me start by introducing the model of random function. For me, a random function will be a combination of deterministic functions. So here we see P and X is a combination of P1X, P2, up to P and X. So these are deterministic functions. There's nothing that is random about them. And then we'll have the coefficients C1, C2, up to Cn. These are random variables. And if you haven't seen random variables before, just keep it an example in mind, like Ci takes the value plus or minus 1 with equal probability. And here is a toy example to keep in mind. P and X equals a combination of these deterministic functions being 1x up to x to the n, and the random coefficients are just the random signs. So another way to think about it is you think about a polynomial Pn up to degree n. So there and the coefficients are either plus minus 1, the 2 to the n plus 1 of them, and you pick one at uniform, and you get a random polynomial. It's going to be the exact same distribution. And random polynomial has been studied since the 1930s, and people in math, physics, and in physics have been interested in studying random polynomials. It appears in quantum chaotic dynamics, and and it has long been found that the real roots of random polynomials are closely connected to the zero crossing properties of the diffusion equation with random initial conditions, as studied by Schur and Machamda in 2007. And it's also applied to the study of persistence probability, which is the probability that a random polynomial has no real roots. And it's called persistent probability because it's related to the persistent properties of physical systems. And Dambo-Marcucci in 2015 used this persistent property, the relationship, to study the persistence probability. It also has several applications in number theory, as shown in a series of papers by Bourgain and Rudnick back in 2010s. And it is connected to a established field in probability theory, what is known as the random matrix theory. And here in this picture, you see on the left-hand side is the eigenvalues of a very classical random matrix model, what is known as the Chinibra ensemble. And on the right-hand side, you see the zeros of a random function. This is also a very classical random polynomial random function known as the Gaussian entire function. And if we look just from our bare eyes, there are many properties of the two models, of the two pictures, and seem like these are indistinguishable just through bare eyes, even though they are, if we do closer analysis, these are actually having different statistics. However, through bare eyes, they look quite the same. And they all have a very interesting property known as the non-repulsion property, meaning if we see a root here, then it's very likely that you find in a small neighborhood of a root, there are no other roots. That's the non-repulsion property. And the random matrix also has similar properties. And in other aspects, random functions have close connections with random matrix theory. And one advantage of random function is that the model looks simpler than random matrix one. So sometimes the approach is a little simpler. Sometimes it's more difficult because random matrix theory inherits nice properties from algebra, whereas random polynomials don't. So that's something to keep in mind. And here are some classical examples of random polynomials. This is the classical Kac polynomial. It's just a random polynomial when the coefficients ci's are random variables. And a more generalized version of Kac polynomial is known as the hyperbolic polynomial. So here are the ci. In our talk, we always assume that these have mean 0 and variance 1, and think about these as the variance of the original distribution, original. So L here is a constant. When L equals 1, then we get the Kac polynomial. And these are important because the roots are asymptotically invariant under the isometries of the hyperbolic planes. And now why is it, why do people care about this polynomial? Because it's invariant under hyperbolic planes. Why is it important? It is because one of the reasons for studying random polynomials is to understand several physics point processes that people observe either in real life or that they see in the lab. And sometimes the point process that we see in the real life or in the lab again, these have some invariant properties. For example, the invariance under some transformation of the hyperbolic plane or the plane itself. And one of the goals of math is to come up with a model that we can actually sample the point process that we see in practice, and we sample them by our models. For example, we sample them by the Kac polynomial so that we can study their properties. Okay. Next, classical ensemble is the Vial, or also known as the flat polynomial, when the coefficients are 1 over square root I factorial. These are invariant under isometries of the complex plane. And then there is elliptic polynomials when the coefficients are square root of n choose I, or invariant under the isometry of the Riemann sphere. And then random Fourier series, of course, these polynomials are cosine and sine functions. And more generally, we have random orthogonal polynomials when the PIs are orthogonal with respect to a measure mu on a complex plane. So these are the most general one, and these appear in approximation theory. Now, when it comes to random polynomials or random functions in general, two of the main questions are with the distribution of the complex roots. So we want to see how they distribute on the complex plane. And the second question, main question, is with the real roots, when we're only interested in the real line. And so we would be interested in what is the average number of the number of real roots. What is the standard deviation? How is it deviate? And what is the asymptotic distribution of the real roots? So these are three particular questions when it comes to the real roots. And most of my research on random function has been focusing on the second question. But let me first start by showing some pictures of all the complex roots. So here I sampled the cos polynomial. And you will see this is a very, so they have a very pretty picture here. So these are all sample root and on the complex plane. And you see that most of them concentrate here around this circle. What is the unit circle? Here is an even more stunning picture that I got from the website of Bayes. And so this is actually for deterministic functions, but it offers a similar picture. So I thought showing this would be a better option. So here they draw all of the roots of a polynomial in which the coefficients are plus minus 1 and the degree n is less than or equal to 24. And it looks very similar to the random picture that we saw on the last slide. And let me zoom in a little bit of this picture. So here is some observation that we see, and these can be formulated into questions. And I would say almost everything is unknown about even about the simple cos polynomial. So in this picture, we'll see two phenomena here. One is the holds here, and these points are at the root of unity, we would guess. And then we see the fractalized structures here. Let me zoom in to see these pictures. So here is the feather-like structure that we saw over here. This feather-like structure. And then we also see the dragon-like structure a little bit up in the previous picture. Yeah, this dragon-like structure here, feather-like structure here. Question is, can we mathematically formulate these properties, and can we prove it? And then with the holes, here I zoom in the hole at one, which is the biggest hole that we would see in this picture. And then let me zoom in at the hole at other points. So through bare eyes, I would guess that these holes firstly have different diameters, and secondly, they have different fractal-like structures.
May I have a question? As I own the structure that people knows, like the fractal structure, you tell us too, right? As I own the structures.
Sorry, can you say that again?
Can you go back to the previous slide?
Yes, sure.
Yeah, you show there are two structures here, right?
Yes.
As I own the structures, or the two of them?
Oh, are they all? I would say no.
So
yeah,
maybe in different places there are different structure, right? Or
I think so.
okay.
I think so. So here, I think that this is the structure deviating from one, and then this dragon-like structure deviates from this roots of unity. I would guess around these points. I, for example, there is a structure. It's just I cannot find the picture on the web.
I see.
Yeah, that's an excellent question.
Thank you.
You're welcome. Thank you. So those are the pictures for the complex plane. So I like to show them whenever I talk about random functions. But let me go back to our tools and what we can actually show. So whenever we have a question with random polynomials, our approach has been two steps. First step is we try to understand the Gaussian case, meaning the case when the CIs are Gaussian, or also known as normal, the bell curve. So these are usually easiest ones to understand because there are numerous tools to use. So we have tools from theory of Gaussian processes. These Gaussian random variables, they have nice computation, they have nice invariant properties on the complex plane. They have nice symmetry properties. So they have many tools that we can use when it comes to the Gaussian. So that is usually the first case that we study. And then for the general distribution, for example, when CIs are plus minus 1, for example, and we try to study the properties of the random polynomials under this case, then what we usually do is to use try the universality, try to show if they have the universality property, which I will explain shortly. And with this universality, we reduce the CI, the general CI, to the Gaussian CI, which I denote by the tutor. So CI tutors are Gaussian. Okay, so this is our general approach, and this approach is originated by a very beautiful paper by Tao and Wu back in 2014, which can be traced back to their study in random matrix theory. And so let me explain what is universality that I mean. So the zeta 1 up to zeta n are the roots of Pn, and we consider a fixed ball on the complex plane. And for instance, we are interested in knowing what is the averaged number of the roots inside a ball, what is denoted by the expectation, right? And the number of roots can be calculated by inside a ball is just the sum of f zeta I, where f is the indicator of the ball. Right? And in general, we would be interested in a statistic like this, expectation of the sum of f of these, a combination of these zeta i's, where f is a smooth function. For instance, f is an indicator of product of the ball, then that will calculate the Kate moment of the roots. Or f can be a product of different balls. That will knowing that will tell us the correlation between the number of roots in different balls. And in order to study a statistic like this, so this is the statistic that we are interested in, and this is the statistic of the corresponding Gaussian. So here the PN tutor is the one when the zeta I tutor are the Gaussian. So this is originally our object of interest, and this is the Gaussian version. And local universality, if holds, will say something like this. The statistic that we're interested in is roughly the same, asymptotically the same as the statistic coming from the Gaussian. To be useful, these bounds should be generally quantitative, meaning the error term is controlled. And of course, the better control the error term will give us a better analysis. This is usually proven for any smooth test function, any fixed smooth test function, and a result like this is called a universality result. And in the past couple of years, we have been using the universality method to study the several statistics of the real roots. Firstly, the expectation, meaning we have a random polynomial. We ask what is the average number, what is the typical number of real roots. And this was studied in a paper by Tao and Wu that I mentioned before back in 2014, and then later more sharp bounds and study for general polynomials by myself, Do and Wu in 2018, and another work by myself with Wu in 2017. And we also use it to study the variance of NN, which was originally studied in a very surprising work by Bali, Caramelino, and Polly in 2018, and then Do, myself, and Oanh Nguyen back in 2019. And in this work, we actually study a very surprising phenomenon of the variance, in which we show that the variance was not universal. And here in this work, it is shown that the expectation is universal for most all classical models of polynomials. But here in this work, we show that for the random trigonometric polynomials, the variance is not universal. And then the method is also applied to study the Central Limit Theorem, meaning showing that the number of real roots, so n and r is roots, and here we rescale, subtract the mean and divide it by the standard deviation so that we get a random variables of mean 0, variance 1, and show that asymptotically that it has a bell-shaped distribution. For the Central Limit Theorem, is actually the hardest question among the three that I here. So here we have three, and of course these Central Limit Theorems are the hardest one because it not only concern the expectation, but also concern the whole distribution of the expected of the real roots. And what is known about the Central Limit Theorem? In a classical result by Maslova back in the 1970s, she showed that for the Kac polynomial, meaning when these coefficients are all 1, and so we just have the monomials here, and we have the random coefficients which have been 0, variance 1, and she assumed that the CIs don't have mass as 0, and show that the Central Limit Theorem holds. Now Dalmau in 2015 showed that the Central Limit Theorem holds for the binomial also known as the elliptic. Doe and Wu in 2018 show it for the Vial polynomial, and Granville Wigman in 2011, Azayet Leon in 2013, Azayet Dalmau Leon 2016 showed the central limit theorem for random trigonometric polynomial. But all these three results are only done for the Gaussian. Now, to prove the central limit theorem for these models of polynomials for general distribution has been a very challenging problem that we have been pursuing for the last couple years, but it has been very challenging to get a better understanding of these problems. So let me tell you a little bit about what the difficulties with these polynomials. Firstly, when it comes to proving central limit theorem, one needs to control all the moments of NN. Not just the expectation or variance, we need to control all of them. So ideally, we would have to show something like this. The K moment of NN is roughly asymptotically the same as the K moment of the Gaussian version. But when we try to show something like this, usually we have to break up the real line into smaller bits so that we can control each bit. And so this statement is like a universality statement. And then we have to add up the error term. Usually, so for our analysis, the error term is not sharp enough to get any meaningful bound when we sum them up. And also, even more challenging is this is not always true, meaning the K moment is not always universal. As I mentioned before, we showed that for trigonometric polynomials, the variance, even in the case when K equals 2, the variance is already non-universal. So that makes it even harder. Now, for this talk, let me talk about our proof of the CLT for the hyperbolic polynomials. We actually proved something more general. We showed that the central limit theorem holds when the AI grows polynomially. Now, let me emphasize that this only works for when the AIs grow polynomially. When the AIs grow exponentially, for example, the elliptic polynomial and the Vial polynomial, this doesn't hold for our work. Okay. So here we assume that, only assume that the CIs have mean 0, variance 1, and finite 2 plus epsilon moments. And we show that the NN satisfies the central limit theorem. NN here is the number of real roots of the polynomial. And so for the proofs...
sorry, quick question. Can you go back to previous slides?
Sure.
So grow polynomial in terms of I or in terms of N?
That's a great question. It's in terms of J.
In terms of J. Okay, because later on we need to send N to infinity, right?
That's right.
Okay, so thanks.
Yeah. So one example to keep in mind is so Pn. So this is the cos polynomial, the sum of Ci x to the I. Now that's the cos, and then there is the derivative of the cos. So I Ci x to the I minus 1. Now this is the AI. So
okay,
AI
I see.
equals I. And generally, if we take more derivative, then AI is I to the rho, where rho is a fixed constant. So these all works.
Thanks.
Thank you. Yeah. So as for the proof, again, we'll do two things. One is universality, and second is to prove the central limit theorem for the Gaussian. And for the universality part, what we prove is to show that the distribution of the general case, the real roots for general case, is the same as that for the Gaussian. And here f is any test function, any smooth test function, and we show that the expectation of f when applied to nn minus that version for Gaussian will converge to 0. And how do we show the universality? Firstly, we partition the number of real roots into dyadic intervals. So intervals of these, the form 1 minus delta over 2. The reason for participating into this small interval is that in each of these interval, one expects to see about an order 1 root. So in this interval, the number of root is usually of order 1. Expectation is of order 1. So these are local intervals that we look at. And for each of these local intervals, we show here is just a rough upper bound. So they are typically of order 1, but a rough upper bound is to show that they are smaller than log, the number of real root in each of these intervals. And for this step, we use the anti-concentration bound that we developed in our earlier work in 2017. And so the number of real roots will be approximated by the sum of these n1 up to nm. So let me draw a little picture here. So here is the real root, and as we saw in the earlier picture at the beginning of the talk, most of them concentrate near plus and minus 1. Actually, very concentrated around these. So here is -1 plus 1 over c, and here is 1 minus 1 over c. In this interval, there are almost no roots here, so there is an order 1 root, so we can forget about them. They will become negligible. So we only focus on a small interval between -1 and 1. Now, in each of these small intervals, we'll divide into dyadic interval. So this is n1, n2, and so on. And we stop at 1 over n. Of radius 1 over n. In this interval, there also only a constant number of roots here. And so these are all of the ni, and the number of real root is about the sum of these ni. So that's the first step, making a sum of random variables. And that is promising because before, in the context of the very classical central limit theorem, the very classical one that you may have heard of, central limit theorem says that if we have independent, let's say IID, random variables, xi, xi, then the sum of xi minus the mean of the sum and divided by the standard deviation, that converges to the Gaussian. This is the classical central limit theorem. So at least this first step is promising in that we have written our n, the number of real roots, into a sum of random variables. Then the next step would be to show that these are almost independent. So to show that, here is just a pretty standard step in approximating these indicator. As you see here in this picture, we have an indicator function of the interval, and we just smooth it out so that we can do some analysis with it. So the phi is just a smooth function that approximate the indicator function. And this phi, we want to bring it to the complex plane. So that's why it has two components. This is the real component that we see on the left, and then the complex component. So here is I, whether we have the complex part. So the real roots is when, so phi I equals 1 when the real part is 0, actually 0 here. And so it's something very tiny here to approximate the indicator at 0. And the tool to go from the indicator function to this smooth approximation, we show the tool is to show that there is no complex root near the real line, so that we can bring the real line to the complex plane. Now let me explain why we want to bring the real line to the complex plane. The reason is because we want to be able to use the so-called green identity, green second identity. So meaning if we have these phi, these are smooth and compactly supported function on the complex plane. If we use the green identity function, this allows us to bring this statistic on the roots back to the original polynomial. So we're good. We only need to deal with our polynomial directly here. Right, so this is more or less our starting point of the universality. And so what we want to show is something like this is universal. So as here is a sum, an integral, then a natural step is to approximate it by just a Riemann sum. In later work, we show that this is not necessarily, but for some intuition, let's say we approximate it by the sum, and for this approximation, we need to show that the variance is bounded, the variance of an integral. The second moment of the integral is bounded, so that we can use some sort of Chebyshev inequality for the approximation of the integral by the sum. Now, in order to show something like this is bounded, this log, so for the upper bound is usually is very easy to bound. It's just apply Markov inequality, but the difficulty comes from showing that the log cannot be very negative, meaning the pi, the pn here cannot be very small. Yeah. In absolute value cannot be very near 0. And so, but with our tools, with our anti-concentration, and something like that is called anti-concentration. And for our tools of anti-concentration, usually we can only show that if at the concentration at a fixed point. And even worse, we only show that for any ball there exists an x such that we can control log p and x from below efficiently, meaning at any point in the ball we can control it, but not with the strong probability, with a high probability. If we want to control it with a very high probability, which is what we need, we can only show that there exists a point at which we can do it well. And back in Tao and Wu, in the work by Tao and Wu in 2014, they also have to deal with, even though their approach was slightly different, they also have to deal with the same issue. And what they do is they prove the same lower bound. They try to prove a good lower bound for every z. And their work is a very, very beautiful proof, but it's also very difficult. They used a dedicated method of inverse Littlewood alpha theory and other very heavy tools from analysis, and their proof is applicable to the cost polynomial because it uses the cost polynomial when the AIs are 1. It has nice algebraic properties, but when we failed to apply their method to hyperbolic polynomials, for example, or when the AIs are not even do not even have a deterministic formula. In that case, it's even harder. Quite happy we've come up with a different approach that only use the tools that we have at hand without having to use the other method by Tao and Wu. So what we do here is we look at the polynomial Pn, take the log, and then we subtract the roots inside the ball that we are looking at. And then we get the log of GZ. Now this one has no root inside the ball, and therefore it is a harmonic function. What else we know? We know that this is bounded from above. This one we can easily control. So this one is a harmonic function that is bounded from above. And then there is the Hana Inequality that says that if we have a non-negative harmonic function, then controlling the function at one point in the ball allow us to control the function on every other ball points inside the ball. So that is the exact tool that we need to control the function from below. Okay. And now that we have reduced to the log function, the next step is to prove that is universal. Like a statistic like this is universal, and that can be done by an argument similar to the classical Central Limit Theorem. Because here Pn, if we think about Pn as just a sum of ai ci x to the I. So let me bring x to the I here. So it's just a combination of independent random variables. And in the context of Central Limit Theorem, it is shown that something like this is already universal. So at this step, we just apply the classical tools here, and we're done. So that is the universality part. The underlying method is to swap one coefficient at a time and add up the error terms. Okay. Now for the second part is to prove the statement for the Gaussian. This is independent from the universality step, and because we are running out of time, so let me stop here and I'll see if there are any questions. Thank you so much for your attention.
Thank you very much. So we have time for questions. Ask any questions, please. So may I have question? Can you go back when you choose delta? In some previous steps, you need to choose some delta. Is that delta depend on n?
Oh, that's a good question. No, it does not. But the typical ones do. Is it in this slide?
Yes, yes. So delta here depend on n, right?
So typically delta does not. So delta takes value from some 1 over c to 1 over n. So some of them don't depend on n, but the typical ones do depend on n.
Okay, thanks.
Yeah. So the typical ones, so we look at all of these, but the typical ones are between 1 over n and 1 over something very big, e to the square root of log n. Something like this.
How can we choose it? Based on what?
Oh, so we show, meaning we want to choose delta as like this range as small as possible, right? And so what we need to show is the one that we omit. So the one between here and here. So these we have to show that it's negligible.
I see.
And we want this to be as small as possible so that we have a better control. The smaller delta, the better we can control the error term.
I see. Thanks. So yeah, we have a question from the audience. What's the reasons for the proof for the Gaussians? So maybe can you quickly show the Gaussian path?
Yeah, sure. So the Gaussian part, we use some ideas developed by Eders in Oxford back in 1956, where they approximate the real roots by the sign changes. So they divide, as we also divide the interval into a very small interval here, then it's likely only one root. So either there is a sign change would contribute to one root, or there is no sign change, then there is no roots. So the number of roots is the same as the number of sign changes. And the next idea is to truncate the polynomial into these terms. So what happened is, for example, we have two small intervals here, and these is the sum from M1 to M2. And then this only concern M3 to M4. So in this step, we show that here, it's even though it's a sum from 0 to n, all that matters comes from some m small x to big M x. And for these intervals that are far enough, we show that this M2 is smaller than M3. And so these are independent, meaning because they only involve independent random variables. And so if you remember our n being approximated by n1 up to some nm here, and what happened is, so we go into text, for example, n1 plus n5 and 10, for example. So some of these are far away, and we show that these are independent by this trick to get independence, and then the rest, so these n2 and 3, so these we show that these are negligible. Actually, this is just some initial idea. Like the analysis, the decomposition is a little different, but this is the idea. In our actual analysis, so here is n1. We take the sum n1 up to n10, for example. So n1 up to n10. We go into disregard n11 up to n12, 13, for example, and then look at n14 to n24, for example. And the ones that we omit is already okay enough that these guys are independent. That's such that this picture works. And then the ones that we omit is small enough that is negligible. So that's the idea of the Gaussian case.
Thank you. Can you see the chat box? There's some questions there. If you can you open the chat box?
Yes,
can you see
it?
Yeah. So we have a question. How big is the degree of the polynomial?
So in our work, the degree is same to infinity. Yes. So that's true, and our work is for n going to infinity, not for a fixed n.
But you mentioned that you can obtain some quantitative errors, right?
Yeah.
So yeah, okay. So you can you send n to infinity, but you obtain some quantitative errors for finite n. Is that correct?
That's right. So our error term, for example,
what is the order of the error terms?
So it depends on the problem. For example, the simple problem of the expectation of real root, then what we show when compared to the Gaussian is of order 1. That is because we have to deal with, for example, the fixed intervals, like from 0 to 1 minus 1 over c, for example. That is a fixed interval, and when we send to infinity, the error term is about of order 1. So it depends on the particular interval that we are looking at. When the interval
can you see
is
the question more? There another, how do you deal with this? Okay. And there another question.
Another question is, I think the last question of the 3, how to deal with the problem for high degree polynomials. Again, these machinery are developed only for the case when n is sufficiently large, meaning our asymptotics works when n is sent to infinity. Yeah, thank you. And any future plans? So there are many questions that are open when it comes to random polynomials, and all of these are, I would say, like almost any question that you come up with for random polynomials, I would say is unknown. For example, only recently we know that the roots at 1, the neighborhood at 1, the whole is of order 1 over n. So that we only know, I would say I only know last month. For example, one can ask, what about other roots of unity? What is the radius of the whole? That is unknown. Another kind of question when it comes to the real roots. So one kind of big projects that I've been following the last few years is to prove the Central Limit Theorem for the Vial and the Elliptic polynomial and the Trigonometric polynomials. So these are wide open. They are known for the Gaussian, but it's wide open for other distributions. Even for continuous distribution is still open. The persistent probability, for example, is that I introduced at the beginning of the talk. It was known for the Gaussian. These results, some of them are known for the Gaussian, but not for general distribution. The persistent probability is known for several class of polynomials, like the Cos polynomial, but some other classical ones is still unknown. Concerning the real roots of the classical polynomials, even the variance is unknown, meaning the Cos is known, trigonometric polynomial is known, but even the variance for the Vial polynomial and the elliptic polynomials, these are unknown. Right? So yeah, I would say almost every question that you think of when it comes to polynomial, they are probably unknown.